Hi class. We continue our study in chapter 2 talking about modeling with linear functions by moving into section 2.2, and this is called finding equations of linear models. So if you remember in the previous section, what we did was we had some set of data, all right, and usually in a table, and we took that table of data and we plotted it in a scatter plot, and what we did was we just drew a line through the data, and we used that line to help us model. Okay, so what we want to do now in this section is instead of just, drawing a line and using the line to model the data, we want to fit some type of mathematical equation that describes the authentic situation. All right, so let's kind of start with an example so you get what I mean. All right, so this is about finding an equation of a linear model. So the number of birds species involved in airline bird strikes has increased approximately from 230 species in 2008 to 330 species in 2014. I know it's a weird example. But what you want to take away here is that, all right, so these airline bird strikes, so that's like birds just hitting airlines, okay, has increased approximately linearly. So that means that the rate of change or the growth of it has been kind of like a straight line. So from 230 in 2008 all the way up to 330 species in 2014. All right, so let's let n be the number of bird species involved in airline strike. Okay, so that would be the 230 and 330 numbers. In the year that is, now this is important, we saw this in last section, T years since 2000. So 2008 would be 8 years since 2000, and 2014 would be 14 years. All right, so I want to find an equation of the linear model. All right, how are we going to do that? So what I'm going to do is I'm going to set up a little table here. So the values of T and N are shown in this table. So I have years since 2000. So 2008 is here, 2014 is here, and then correspondingly the number of birds species are here. So 230 and then 330. All right, so going back, I want to find an equation of the linear model. So that whenever I say linear model, that tells me I want to find the equation of a line. All right, well, I've got 2 points here, basically, okay? T is going to be my independent variable and N is going to be my dependent variable. So I know this is weird, but think of the T as my X, the N as my Y. All right, so to find the equation of a line, you need two things. You need a point on the line. Well, that's great, I've got two of them. But then I also need to know the slope of the line. Well, I can find the slope of the line from these 2 points. All right, so the slope is the change in y, which we're just calling n, which is, we'll use this one as my y2 or x2, y2, x1, y1, but it's really t and n. So it's 330 minus 230 divided by the change in x or the change in t, which would be 14 minus 8. So you get 100 divided by 6. And you'll notice in this case, I'm going to actually just say it is approximately, like if you take 100 and divide it by 6 in your calculator, you'll get 16.666666 repeating. So I'm just going to leave this as 16.67. I'm going to round it off here. Okay, so I've got my slope of the line. The next thing I'm going to do is I'm going to set up my equation. Remember, my equation is y is equal to mx plus b, but here we're calling yn, we're calling xt. So I'm going to plug in the slope I just found for m here, 16.67. And then what I'm going to do, I need to find this intercept here, in this case the y-intercept or the n-intercept. I want to find the constant b by substituting the coordinates of, let's just take the first point, 8 comma 230 into this equation. So 230 is going to go in for n, remember, and 8 is going to go in for t. So now you're just going to multiply here, get basically 133.36. You're going to subtract it over to the other side, and you're going to get 96.64 is equal to b. So now what we know is we can substitute this b in for the y-intercept or the n-intercept. And my equation here is the number of species of birds, all right, who are involved in airline strikes is equal to the slope, the rate of change here, the 16.67, times the number of years since 2000 plus 96.64. All right, so we can verify this equation using trace on our graphing calculator if we want, and check. You can see that the line that we made approximately contains these points. So I'm going to show you on your calculator how to do this actually with the table. It's a little bit easier. So what I'm going to do, I'm going to take my graphing calculator. I'm going to hit y equals, all right? So remember, y is my n. So it's 16.67 times t, which is just my x variable, plus 96.64. So I'm going to graph this. All right, you're going to notice when you do this that you don't really see the line. It's a little weird. So I wanted to show you how to zoom out in your calculator. So you can hit zoom. There's all these different options. I want to do zoom out number 3. You just press number 3 and hit enter. And you can keep zooming out. All right, and then you can see you zoom so far out, you know, just not really the greatest picture of it. But that's okay. So I'm going to go back and look at the table numbers here. Look, if I scroll down to my table and get to 230, look, it's right there. If I keep going down to 14, look how close it is to the real value. All right, and the reason it's off just a little bit, by the way, is because we rounded the slope. All right, so this was good. We did it with just 2 points. That's great. All right, let's take a look at another example. All right, so this is finding the equation of a line from a bunch of data. So the percentage of new vehicle transactions that are leases, so these are leases, not purchases, are shown for various years in the table to the right here. All right, so I'm going to let P be the percentage of new vehicle transactions that are leases. So this percentage here is going to be just the number P. All right, that are leases. Now this is important. At T years since 2005. So T years since 2005. All right, so basically 2009 would then become 4 and so on. So let's find an equation of a line that comes close to the points in the scatter plot of the data. All right, so what I'm actually going to do is we're going to view the scatter plot using a graphing calculator to save some time and some accuracy. So you can see this is the scatter plot, and I'll talk about this in a second. So what I'm going to show you in your calculator is now how to do this. So I'm going to go back to my table of data. All right, first thing you have to do this, all right, let's just click, this is important here, let's click the y equals button first, and let's clear this line out, because we don't want it in our graph anymore. So it's cleared out. The next thing I'm going to do is this button will become very important throughout the class. I'm going to click this stat button right here on your graphing calculator, stat. Now what stat does, the most thing we're going to use the most is this option called edit, and then over in calc, we'll later on at the end of this lecture use this thing called linreg, and I'll talk about that. But edit, number 1 here, so under number 1, you're just going to hit 1. And you should see something like this in your calculator. And this is incredibly important. You should see L1 up here and L2 up here. L1 is always going to get the independent variable. Well, the independent variable in this case is the T variable, the T variable. So T is years since 2005. So 2009 is 4 years, 2010 is 5 years, 2011 is 6 years, 2012 is 7 years, 2013, excuse me, is 8 years, 2014 is 9 years, 2015 is 10 years, and 2016 is 11 years. So then over in L2, that's always going to be your dependent variable, or in this case, the percentage P. So I'm going to put in 14.8, 18.6, 20.6, 19.6, 22.9. Notice I'm just going down the table. They have to correspond to the accurate value. 25.6, 26.7, and then finally 31.6. Okay, 9 times out of 10, if you see an error in the next thing I'm going to do, it's because you didn't input the data correctly. So just keep that in mind. All right, the next thing you're going to do, this will take a second to watch, and you can rewind and check the settings again. But you're going to hit second function, and you want this stat plot. So you're going to go second function, stat plot. You're going to notice something says plot 1 ... off. Okay. What we need to do is we need to turn this on. So under number 1, I'm just going to hit enter. And then all I have to do is make sure that this now moves over to on. So I just hit enter at on there. The next thing you're going to do, all right, is your graphing calculator is currently zoomed for the previous example. So you're going to click the zoom button next. And what you want is you want to scroll down so you see this thing called zoom stat. And then you're going to hit enter. And look at this. Does this look exactly like this on our graphing calculator? Yes, it sure does. Okay. So you can use this graphing calculator, which is great, or you can even use the StatCrunch I showed in the previous video to this one, but your graphing calculator is a great tool. Okay, so I'm going to talk about this now. So what I want to do is I want to fit this data, okay? I want to fit this data with a model, okay, that describes the relationship between the variables, okay? And what I want to do when I'm going to eventually find the equation of a linear model is I'm going to draw a line that goes through 2 points, okay, on the graph. So notice this red one is not a good model. So I picked the first 2 points. And the line that goes through the first 2 points, like this, not great, pretty terrible. But when I pick the line that goes through this point here, 4, 14.8, so basically this point right here, the 2009 starting point. And then the next one here, 9, 25.6, this one right here, which is over here in 2014. We see that that line actually does a pretty good job going through the data, right, or modeling. So basically what we're seeing here, right, is that for some reason, since 2005, the percentage of car sales that are leases has just gone up. And it's gone up in kind of a linear fashion. And this green line that goes through this point and this point does a good job modeling the data, all right? So now what I want to do is I recognize that this green line is a good model for the data. Right? I want to find the equation of that line. All right, so we want to find the equation of that line that comes close to those data points. All right. Now I did pick 2 data points, but recall it's not necessary to use 2 data points to find an equation. Okay. All right. It's often convenient, but you could pick some points that are not on there. But for these simple examples, you're going to want to pick points that are actually in the data set. So the red line contains the first 2 points, does not come close to the other data points. However, the green line, as I said, that passes through the points 4, 14.8 and 9, 25.6 appears to come close to the rest of the data points. So we'll use this equation to find the line. All right, so got the 2 points. Remember, this is my T and P, or X and Y. So the first thing I'm going to do is I'm going to find the slope. So it's the change in the dependent variables, so 25.6 minus 14.8, divided by the change in the independent variables, 9 minus 4, you get 10.8 divided by 5, right? Which is a little off here. Okay, so this should actually be 2.16. Sorry for the error there, 2.16. The decimal place is incorrect, 2.16. All right, so now that I knew the slope was 2.16, sorry for that typo there. Substitute 2.16 in for m, all right, into the equation. Y is equal to mx plus b. We're calling yp, and we're calling xt. So I'm going to pick, I got to find the intercept, so I'm going to pick one of the points, all right? So I'll pick the first one, so the 4 and 14.8, and I'm just going to substitute them into the equation. Multiply here, all right, 2.16 times 4 gets me 8.64. Subtract it over to the other side, and you get the intercept is 6.16. So I'm going to substitute this in, 6.16 in for b, and this is the equation that I come up with. P is equal to 2.16t plus 16.16. And that is the equation of that green line, right? So now what I want to do is I want to check for correctness of the equation right, using a graphing calculator to verify that those points that I came up with, or that equation of this line right here, actually goes through um, uh, the data points. So what I'm going to show you here, this is the line plugged into our graphing calculator, actually subbed right into the graphing calculator. So I'm going to show you how to do that. So you should have your graphing calculator loaded up with the data set in here. So to plug this equation of the line in, just go back to your y equals button and just literally plug in the equation we just found. 2.16 times the independent variable plus 6.16, and then just hit the graph button. All right, does that line do a good job modeling or going through the data? Absolutely. Yes, it does. It's a great line. Okay, just want to talk about some common things here. Okay, so it is common error to skip creating a scatter plot, right? But you should always create a scatter plot when you're given data, all right? First off, you can look at the scatter plot and determine whether the data is approximately linear. We're going to do examples later on in the class where things are not approximately linear, so you're going to have to look at the scatter plot first. Okay, also, if so, it can help us choose 2 good points to find the linear model, all right? And by graphing, we can assess whether the data fits the model well, right? So that equation that we find by plugging it in. Okay, so just how to do this. Find an equation of a linear model, right? When you're given some data. First, construct a scatter plot of the data. Determine whether there is a line that comes close to the data points. If so, choose 2 points, not necessarily actual data points from the graph, but that's the easiest thing you can use to find the equation of a linear model. Next, 3, find the equation of the line by using the 2 points you just found. And then the last thing is use your graphing calculator to verify the graph of your equation. All right, make sure it comes close. All right, this is how you can do it by hand. All right, this is how you can do it by hand. However, the graphing calculator has this feature that will actually do it for you. All right, so most graphing calculators have a built-in what's called linear regression feature for finding the equation of a linear model. And a linear regression equation found by linear regression is called, or linear equation found by linear regression is called a linear regression equation. And the function described by this equation is a linear regression function. All right, and the graph of this line is called a regression. So it turns out that, let me go back. I want to show you a graph. Where are you, graph? When you draw a set of data, there's actually an infinite number of lines you could draw through this. So we see that this is not a good model, but this is a good model. Is there a better model or a best model that fits the data? And yes, there is. And your graphing calculator will do this for you. So looking back at this line right here, okay, something called this regression line. Okay, what is the regression? All right. Well, first off, let me go into this y equals button and clear this out. So notice what we had here. We had 2.16x plus 6.16. All right, keep that in your mind. I'm going to click this stat button again. First thing you have to make sure when you're going to use linear regression under number 1 is that you have data plugged in here. Okay, that you have data in L1 and L2. Next thing you're going to do is you're going to hit the stat button. You're going to go over to calc, and you want number 4. You want to see this thing called linreg, this ax plus b. So hit 4. If you have, this is an older TI-83, it says linreg ax plus b. At this point, you can just hit enter. If you have like a TI-84, you're going to see like, it's going to say list 1, L1, list 2, L2. Just hit enter until you get down to the calculate. Watch what happens when I hit this, okay? This is saying, look, the line that best fits the data, y is equal to, they call it ax plus b. They're saying the slope, a, is 2.1, and the intercept, b, should be 6.8. So the line that best fits the data is actually y is equal to 2.1x plus 6.8. Or in our case, the percentage of car leases is equal to 2.1 times the number of years since I think 2005 plus 6.8. Let's plot this line here in our graphing calculator and see what it looks like. So it's y is equal to 2.1 times our independent variable plus 6.8. Now watch what happens when I hit graph. The line we picked used this point and this point. Well, it turns out that the line that actually literally best fits the data is this line right here. There's no straight line that better fits the data than this one exactly right here. So you'll want to use your graphing calculator for these going forward.